All right, howdy y'all. So we're going to be showing that the I1 from 8.15 is bounded by a delta with A independent of delta. So there's a ton of algebra in this one. It is just disgusting amount of algebra that you need for this one. And I'm not meaning like modern algebra, I mean like pre-calc. So bear with me, it's going to be a long one. But the geometry of the problem and the setup is pretty simple. So what we're going to do is we're going to let K, capital K, be an integer such that nu over t is in between the K and K plus 1 exponent of t, assuming that n is between, that nu over t is greater than 1. If not, we're going to take K to be equal to 0 when it's less than 1. Now, you'll remember from the prior video, nu was the arbitrary number greater than 0 that guaranteed us that our integral with y less than r is less than delta Rn whenever r is less than nu. So this is in a sense a bounding property. So what we're going to be doing is we're going to be breaking the problem up into shells. So we're going to be taking the shells of the unit spheres, going down all the way to a certain center one, and then we take the ball in the middle. So we're going to define our YKs to be our shells. So we have that Y such that to the negative K, or so that we're going to take all the Y's such that the magnitude of Y is between 2 to the negative K and 2 to the 1 minus K. And then we're going to do this for all the K's less than our capital, small K's less than our capital. Then what we're going to get is, by definition, the ball of size nu around 0 is equal to all the union of all of these shells and the ball at the center, right? So pretty straightforward geometrically. Then what we're going to do, the idea behind this proof is that we're going to be breaking I is an integral, we're going to be breaking I up across the shells in the ball, and then using different the two different boundings that we have to break up the different parts. So the first thing that we're going to do is we're going to say we're going to get phi sub t of y is less than ctn, this guy here, and this is because in the first video we had that phi of x was less than c times 1 plus the magnitude of x, n minus negative n minus epsilon. So because that one is phi and this one is phi t, we end up with the negative t to the negative n on the outside, and we end up with the reciprocal of t on the inside. Then we can replace y over t with this guy here, which is the upper bound on a given in a given y sub k. So we're replacing the function. We're noting that this guy on that particular shell, so on yk, is bounded here, and then on the ball at the center, we get a stricter definition because we notice that we have that n over t is greater than 1. So when I take, or sorry, we get that t to the k is less than this guy. So when I take k outside of the, k was bounded by here. So when I get to the center one, this thing is going to drop below these guys. This thing becomes less than 1, and I can remove it and keep the inequality. So now what we're going to have is we're going to get that I1, which again was the integral here, we're going to break it up across the shells and across the sphere. And again, we pulled out that's a mistake. Okay, no, that gets dropped there. That's why. Okay, cool. I just figured something out. I was a little confused why that was there. Okay, there we go. So we drop off the phi t's That makes a lot more sense. We drop off the phi t's there because we now have bounds for them. So we replace them with their upper bounds here. For this one, the sum across these guys here and here. So we drop out, should that be? One second, no, so this one should be here then, okay, that's why. So what we're going to get now is ct to the negative n times this guy here, so 2 to the negative k nu to the negative n minus epsilon over t. Cool. Sorry, I've been looking, this is the third try on the video. I kept realizing there was mistakes and it all just suddenly clicked. So I'm really excited right now. So we replace these phis here with their bounds, and now we're just integrating across the first part, which was this guy here. However, we have knowledge of the bounds on those guys as well. So what we're going to do is, if you can see down here, let me double check to see if the camera is catching the lower board. And yeah, there we go. Okay, so I got the first couple lines at least. Making sure that it's visible in the video. Okay, cool. So what we're going to get now is that we can replace the integral altogether by the measure of the shell times this guy here, the bound on phi, and we have our bound on f of x minus y minus y, which was, where did we have that bounded? We had a bound for that already. Give me a second. Okay, cool. So we know that that thing is bounded by delta. So from the beginning of from the last video, we have that it's bounded, that each of these intervals are bounded by this guy here. So we're going to be replacing that with the bounds on, because we're saying that y is less than r, so we're going to replace it with the upper bound on this guy, which we now have dropping. So what we're going to get is that we have the there's so much algebra in this thing. Oh, right. Okay, so we have here that we have this guy bounded by r, which means the actual function here is going to be bounded by delta. So we can swap that out for delta there, and delta times this guy here, which is our bound from that on f, f of x minus y minus y. Okay, so now that we've replaced the integrals with a pure sum, all we have left to do is to factor everything out. So what we're going to be doing is we're going to be using an expansion on the sum and start factoring. So we're going to, here, we notice that this is with respect to k, and we pull this t out, cancel the two t inverses on n, because this one is in the bottom, so it's going to go to the top, so the n's cancel. And what we're left with is the t to the epsilon, which is here. And then we do the same thing with the 2 to the k's, and we're left with 1, 2 to the k to the n here, and we get that and then the nu is going to cancel with this nu, and we're going to just end up with nu. So we end up with the nu and the t only being to the negative epsilon, and we end up with the rest of this guy we don't alter at all. So now we have this sum here, which we will remember. They use an identity for the sum of exponents of t to replace it here with this guy, right? And now all we have left, let me pick up the video, the board. All we have left, now that we've replaced this, we no longer have a sum. We notice that there's a delta here and a single delta here. So we factor everything out, and we're left with this equation here, or sorry, this algebraic expression here, which we notice has no deltas in it, and we factored out the delta there, and we now have exactly what we were looking for. So this guy here is our A, which is not dependent on delta. Delta is going to 0, and we now have a bound on I1. Sorry, that was a ton of algebra. I'm glad it finally clicked. It took me like two and a half hours looking at this. But I will see you guys in the next video. Unfortunately, the next one's very similar. We're going to be doing it for I2, which we remember was when y, the magnitude of y is less than r. We're now going to be looking at when the magnitude of y is greater than r. It's still just a bunch of algebra, but we'll be done with the theorem. Hate this theorem. And the next two are going to be much more straightforward standard theorems where we're going to be looking at where there's going to be a lot less algebra. Okay, well, I will see you guys in a bit.